All right, so on this Geiger one, it talks about you get 33 particles per minute. Okay, but then it asks about what's the probability something in 1 second. Well, here's my question. How many would you expect in 1 second? So the way to set this up is to go 33 particles in 60 seconds is equal to x over 1 second. You with me on this? Where x is your expected amount. So lambda, some books call it lambda, some books talk about it as mu. I teach this class like 3 different ways. I can't remember the way your book talks about, but that's the expected value or the average. Okay. Now, you didn't talk to me about which calculator you use, so I'll do it both ways just for a good time. So I'll open up my calculator here. So actually, what I'll do is I'll open up 2 of them. I'll do them side by side. Boom. There we go. I'll turn this one into an 83. Okay, so first things first though. So I want to cross multiply and divide, so it's 33 times 1 divided by 60, so 33 divided by 60 is what it really boils down to. So I'm expecting 0.55 particles per second. Okay, that's my lambda, my 0.55. Okay, that's what I'm expecting. So the question is asking what's the probability that I get 1 given that I'm expecting 0.55. You with me on this? So when we do it in our calculators, let's do this one first, I guess. So apps, again, I'm not sure which one you're using, so we'll go this way first. Boom. So I'm going to do the Poisson distribution. And did it say exactly, or did it say it says at least 1? Yes? It says at least 1. Now remember, what is the probability whenever I say at least 1? The way you want to do that is to go 1 minus the probability of 0. Okay, so I'm going to ask the computer is, all right, it's a Poisson CDF. I could do it a couple of Poisson PDF is the way that I would do this. So I'm expecting 0.55, and I want to know about getting 0. Okay, so this is one way to do it, and you'll see that it's 0.577. Let's call it. So that's this part right here, 0.577. And then 1 minus that would give us, obviously what we need. So that's one way to do it. I'll do that minus in a second. You can also do it this way. Here's a problem, though. But we can get a pretty good approximation for this. The number, oops, did I click on binomial? I clicked on binomial. Sorry, let's try that again. There it is, Poisson CDF. So 0.55, this is true. Let's go from 1, and notice that you can't go to infinity, but you could ask about something like 10,000 or something. When you do that, you will find that it's about 0.423, which, lo and behold, is the same as what you get when you subtract those guys. You see that? So that's the answer that you seek. Now, in the TI-83, it's the same process, of course, but you're going to go to distributions, Poisson. And again, I would do it this way. And then, so again, you have to remember what it's asking for. So it wants to know 0.55 is what you're expecting. And we want to know about 0. All right, and if I just do 1 minus that. What happened? Oh, that's what happened. 423. Okay? You should also do the CDF in this deal as well. And same basic procedure, so you're expecting 0.55. You want probability going from 1 to, and then pick a big number. And it doesn't even like that. So I can go back in here and get rid of a couple of those, and then it still doesn't like it. So I'll do it this way. I'll try it this way. To be honest with you, I would never do it this way. Yeah, it doesn't like it at all. Oh, wait, stop. I lied to you. I'm so sorry. Oh my gosh. I forgot. This one doesn't do it that way. So in this one, I have to think about how to do it. The problem is I run too many blame calculators. So 0.55, comma, if I do 1, that's 1 or 0, so I just want just 0. And there it is. So 0.576, and again 1 minus that. This would have been more helpful, which is not very helpful at all, if you only do it with one thing, 0. If you said greater than 3, then I could put a 3 right here. I would get rid of less than or equal to 3, and away you'd go from there. Okay, so that helps with that one, I hope. Another one that you mentioned was, if I can find it, open with, come on, there you are. I had a kid. So the life expectancy of months has a probability distribution that is defined by that thing, 1/2 e to the negative x over 2. Nice. Find the probability that a randomly selected component will last between 14 and 12 months. Give your answer as a fraction or a decimal of at least 4 places. Okay? Pause for just a second there. All right, and so for the next one, as I was saying, this one here that you sent, about this one here, this is the PDF. And for reasons that are not entirely clear for you, maybe because you don't know calculus yet, to get to the CDF, the actual CDF is going to be this. Okay? And that's, you just take that to the bank. Well, if that's the CDF, remember this is the area to the left. So if I want to know the probabilities between 0, oh, for God's sakes. Oh, no, there it is. I want to know the probabilities between 14 and 22. So the probability that x is between 14 and 22. I literally take I put in, this is some function, we'll call it p of x function, I guess. So we'll do the p of 22 minus the p of 14. Okay? And what that's saying is this, whatever this function looks like, and I'll just draw a picture because it looks something like this. I'm going to go out here to 22, and it's all of this area, right? And then I'm going to come out here to, doggone it, and I'm going to come out here to 14, and it's going to be this area here, and I'm going to subtract them, and what I'm going to get is this piece in here. Okay? So take a calculator, and I personally like this one, but you do what you want to do. So I'm going to do 1 minus, and then e to the negative 22 divided by 2, and hit enter, and I get that number there. So basically 99%. And then I just go back in and change that to 14, and so, oh shoot, idiot. And so what I'm going to do is go up here and grab this guy minus this guy. It says about 0.000895. That's the probability between there and there. Okay? If you know anything about calculus at all, another way to do that problem is to integrate right here, to integrate that guy, and then just go from 14 to 22. But again, if you know anything about calculus, you can't do it that way. Come on, Betsy. Bam, there it is. Okay? But again, that's all you need to do is follow the answers, kind of the idea that they give you in the text, which is the part I was reading about. For instance, if you want to go check it out in the book, is like, well, let's see, it's on like page 333. Solution 5.13 is very similar to that. You can kind of see how it works. And then one of your other ones that you wanted to see, if I can find it, where did it go, is this guy. Holy cow, that's a lot. All right, so planet Pern lay eggs. Oh, the dragons. Oh, the dragons lay eggs. They're green or yellow. 17% are yellow. The rest are green. That's 83% green. So far, it sounds very binomial. All right. The lead scientist, permission to read it, it's going to take 59 eggs to incubate. Consider all the possible samples of 59 dragon eggs. Okay? So, think about that now. So, holy cow, how many different eggs can he get? Well, we don't know, but there's a lot of them, right? So I don't know how many eggs there were to start with. If I did that, I could do a combination. That's not what he's asking about. So what is the mean number of yellow eggs in 59 eggs? Well, I don't know, but 59 times 17 would give you that mean number because it's n times p, okay? And so 59 times 0.17, so about 10.03 eggs we would expect to be yellow. And the rest of them, of course, we'd expect to be green. Now, I didn't ask us for that, but I'm just telling you. So it would be like basically 49 of them I'd expect to be green, okay? Now, what is the standard deviation of yellow eggs? Now, remember, standard deviation for a binomial is the square root of n times p times q. So our n is 59, our p is 17%, and our q is 83%. So if you're smart, you'll just take, there's NP already, just times that by 0.83, and there's your variance, and then square root that. And there's your standard deviation, 2.885. Okay? And of course, to 2 decimal places, that'd be 2.89. Okay? It says to at least 2 decimal places, so you're good there. What is the variance of the yellow eggs? We already did that. It was whatever that was a minute ago. I had it on the calculator. No, try again. The variance was 8.32. Okay. And the last one you asked about was somewhere. There it is. Wow, here we go. All right, so race 9 women, 8 men. Sounds like 17 people. Okay. If your answer is very scientific, okay, what's the probability the top 3 finishers were all men? Okay, well, it's a race, so order matters, yes? So here's the deal. I've got 17 people. Okay, we're talking about the top 3 finishers. So 17P3, right? 17P3. Now, okay, there's 2 ways to look at this problem. So let's think about this first of all. It just says the number of ways they could finish. Okay, probably the top 3. It didn't say what order they finished in. It's what it sounded like at first, but let's go with that for a second. It says, what's the probability that they were all men? It didn't say what order they were in. It's just the fact that they were men. Okay? So there's 17 people. We're choosing 3 of them to finish the race. And so we simply want, actually, I'm going to go look up, see exactly. This question is one of those ones that's a bit ambiguous. If it was a committee, it would. All right, so I went on and I just wanted to double check what the book was saying, so, or what the answer was looking for. So it is, they don't care what order they're in, which is sad. I would never do this to you on a test, because if a race implies order and a race implies permutations, so I would never do this to you. But here's the idea. Just reach into a hat with 17 people in it and select 3 men. Okay, all 3 of them men. So there's 9 men, you're choosing 3 of them. There's 8 women, you're choosing none of them. Remember, the ones on the left, 9 plus 8, add up to the left on the bottom. The numbers on the right on top, add up to the right on the bottom. Anyway, if you do this, you will see that this comes out to be, and by the way, 8 choose 0 is just 0, or is 1 rather, so there's no reason to do that. So second math, 7, assuming you're doing it on this one. If you're doing the other calculator, you've seen how to do it. So 9, 3, that's my numerator, and then my denominator is 17, 3, and then it's just 84 divided by 680 there, diamond enter, and it gets you 0.123529. Okay, and that should be your answer. Okay, hope that helps. And then, all women is similar, except that it's going to be 9 choose 0 men, or I'm sorry, I had that backwards. That was the women. So 9 choose 0 women, and then 8 choose 3 men. Still out of 17 choose 3 people. 2 men, so 8 choose 2. 9 choose 1 women out of the same denominator. And then 8 choose 1. 9 choose 2 women. 17 choose 3. And unless I'm mistaken, right, if you think about it, there's 3 people. You could take no men, one and 3 women, or you could take 1 man, 2 women, and 2 men, 1 woman, and 3 men, 0 women. So this probability, each of these probabilities better add up to 100% when you're done, because that's all there is. All right, let me know if you need some more help.